And from here, we can define the norm space. So definition. So we define the norm space to be a vector space V with scalars F that we know is either R or C and a function of the norm. Wait, sorry. A vector space V with scalars from F and that equals R or C. And the function. So this means we need only one input, and this maps from V to the real number space. And that should satisfy four properties. So for all x, y, it belongs to V, and alpha belongs to F. So the first one is homogeneity. So that means if you want to take a norm of a alpha multiplied by x, then it's the same thing as you take the absolute value of alpha multiplied by the norm of x. Second one is triangle inequality. And that's what we did last time. X plus y norm equals x norm. I mean, smaller than or equal to norm of x plus norm of y. Okay. And 3 is the non-negativity. So that means the norm of a vector is greater than or equal to 0. Okay. And 4 is the degeneracy, non-degeneracy.
So this is just like so is the normal space, like, do you mean it, like, I guess what does the function represent? The function that maps from V to R.
Yes, that's the norm function. We defined it to be the square root of
X,
yeah,
x squared. Is
right.
it x
Or
squared?
actually use inner product like this.
Yeah. Okay.
So we actually have a proposition saying if V is an inner product space, then it's a norm space because all of these properties we can see these in the inner product space.
Yeah.
So
but there are more properties in
inner product space.
the inner product space, yeah.
Yes. V is IPS implies that V is a normal space. But if V is a norm space, it does not necessarily mean it is a in the product space.
Yeah.
Right. But you can basically define any function and from that maps from V from input that belongs to V and the output belongs to the real number. And if what you define can meet these four requirements, then you can say what you define is a norm function. So norm but not net products. So let's see, our vector space is either R to the nth power.
Yeah.
Thanks. Or the complex number. And we define a P norm. And P equals like 1, 2, 3, 4 of those. Right. And now, so this equation, the norm would be P norm of X vector equals X1 absolute value raised to the p power plus X2 absolute value raised to p power all the way to Xn absolute value raised to the p power. And after you sum it up, you take the 1 over p to the whole thing. And in this case, for example, if our X is -1, 2, then if I want to take the 3 norm of this X vector, then it will be -1 absolute value raised to 3 plus 2 absolute value raised to 3, and then take 1/3 power. Okay, this will equal to 1 plus 8, 9, and 9 to the 1/3 power. Okay. So, so this definition is also it can also be a norm space. So we can check every n1 through n4. So let's check for 3, for example. So n1, if we have a alpha times x to 3, then this will be, let's see if I can do it to the p. So this will be alpha x1 plus alpha x2 plus all the way to alpha xn raised to p. Okay, so So basically for each term, we have a alpha to the raised to the p power. So then we can take n of them, alpha raised to the p power out. And then what we have left is the x1 plus the plus xn raised to the p power. Okay, and then you have this whole thing raised to 1 over p. Oh, yeah, if you factor it out, there will not be an n. Okay, now we have a alpha raised to p power, and we have a 1 over p. Okay, so then we can take this alpha out. And then what's inside would be x1 through xn. So these is the definition of the p norm. So this will equal to times the p norm of x. Okay, and now it satisfies the first property of norm space.
Yeah.
So actually there is a theorem in a product space. It's called the parallelogram theorem. So that is from the triangle inequality. So after the triangle inequality, there's a lemma saying that for x, y, and v is in a product space. Then we would have the norm of x plus y squared plus the norm of x minus y squared equals to the norm of x plus the norm of y squared. No square. Inside.
Mhm.
And for this p norm, we can check if we can find like two vectors. So check parallel identity. Okay, so if we want use two vectors, x equals 1, 0, 0, 0, and y equals 0, 1, 0, 0, 0. And they all belongs to the complex vector space. Okay, and now let's check one norm. Okay, so on the left we would have the x plus y squared plus x minus y norm squared. And that in this case equals norm of 1 square. Wait, so 1, 1, 0, 0. So we basically just add these two vectors and plus if we do the minus, then it would be 1, -1, 0, 0. Okay, that we can compute. This is the one norm. So equal to 2 square plus 2 square plus 8. Right, and then we calculate the right-hand side. So right-hand side of the triangle inequality says it should be equal to 2 multiplied by x norm plus y norm. Okay. And this would be equal to 2 multiplied by 1 square plus 1 square. That equals 2 multiplied by 2, that's 4. So we know that left-hand side does not equal to the right-hand side, meaning that parallelogram and identity does not hold.
Hello?
So this theorem of this, so say if V is a norm space, if and only if the norm satisfies the parallelogram identity. All right. So in this chapter, we assume V is an inner product space. So definition for U and V inside this inner product space V, we say these two are orthogonal or we write as U is orthogonal to V if the inner product of U and V is 0. So for example, in R2, we all know that this means the V and U, they form a 90-degree angle. So that the cosine of them is, the cosine of this angle is 90 degrees. And that would be 0. Okay. So, and then we have a proposition, and that's the Pythagorean identity. So that's if we have U orthogonal to V, then the norm of U squared plus the norm of V squared equals the norm of U plus V squared. So quick proof. We know that the U plus V,
I guess,
mm,
is there any way to, like, if I were to visualize the
mm,
norm,
mm,
like the norm of a vector,
yeah,
is it, well,
it's
I
a
mean, as a scalar, right?
yeah, it's the length of the vector.
The length of the vector is the norm. Oh,
Yeah.
yeah. Oh, I see.
Mm. So U plus V squared, we know that equals the inner product of U plus V and U plus V. Okay. And that's by linearity equals UU plus VV plus UV and VU. Um, okay. And now we know the UV and VU, they are conjugate symmetry, conjugate symmetrical. So it will be equal to U norm of U plus the norm of V plus. So UV, we know that U is the sound is off here. We know that U is orthogonal to V, and by definition, U is orthogonal to V means the inner product is zero. So then we can write UV in the product to be zero. And same thing for VU, it's a conjugate of zero, which is also zero, because zero is a real number. So what we have left here is the U and V themselves.
Mhm.
Okay, and now after defining the orthogonality of vectors, we also have orthogonality between vector to a subspace and a subspace. So definition. Hmm? E belongs to V, and W is a subspace of V. All right, and we say V is orthogonal to the subspace W if V is orthogonal to every W for W belongs to V, belongs to this capital W. Okay, similarly, we have orthogonal subspaces. We say let U and W, they all be subspace. they're all subspaces of V. And then we say U is orthogonal to W if for all U in U and for all W in W, U is orthogonal to W. If we are in R3 and W can be the span of say, for example, let's just say 1, 0, 0. Okay, and with a vector, so W basically is like any vector that's on x-axis. And our V, so we can pick any V. For example, let V be 0, 1, 0. And we can say this V is orthogonal to this W because for any vector in W, it is orthogonal to V. And in the second definition, so basically the same thing if we are in R3. And we say the W, same thing, is the span of 1, 0, 0. But for U, it's not just a vector, it's the span of 0, 1, 0. Okay, so then for any vector in W, for example, 2, 0, 0, and for any vector in U, for example, -5, 0, -5, 0, these two are orthogonal. So then we say these subspaces are orthogonal to each other. Yeah.
So I guess orthogonal subspaces just have properties that are like useful. So it's like
Mhm.
wait a second. So does orthogonality only apply to inner product spaces?
Yes, we define them in the inner product
Yeah.
space. We have a proposition say let W equals the span of W1 through WK. And then a vector V is orthogonal to W means that if and only if V is orthogonal to any WI. So the source subspace of the span W1 through WK means that any vector in the subspace W is a linear combination of W1 through WK.
Yeah.
So then if V is orthogonal to any one of them, then it will be like it will be also orthogonal to the linear combination of them based on some linearity of the inner product space or the P4 of the inner product space. We have another definition on the orthogonal system. So we define vectors Vi through Vn form a orthogonal system. Vi and Vj are orthogonal for any I and j where I does not equal to j. And in this case, we also say they are pairwise orthogonal. So example of this can be bases in R3. So we have E1, E2, and E3. So any two of them are orthogonal to each other. Because E1, E2 equals 0, E2, E3 are orthogonal, and E1, E2 are orthogonal. E3. And actually, these three vectors are also called orthonormal because the length of them are 1. So their definition, an orthogonal system orthonormal. Oops. All right. Now proposition. So any orthogonal system of non-zero vectors is linearly independent. So short proof of this. So for linearly independent, we know that we can do a linear combination equals 0, and then all the factors has to be equal to 0. So let's say alpha v1 plus all the way to alpha vk equals to the 0 vector. Okay. And then let's take this whole thing, alpha 1 v1 plus all the way to alpha k vk. And we do the inner product with any vi in this. So this inner product becomes the 0 vector inner product with vi. And we know that will be 0 because of P4. Where's IP4? Okay, 0. Okay, now we can rewrite the left side to be, so we want this, so this left side would be by linearity, by that IP2, we can rewrite it as alpha 1 VI VK plus plus alpha K VI VK VI. And so basically the left side equals the right side equals 0. Okay, now we know that by orthogonality, these inner product will all be 0. The only thing left here is inside of here somewhere, there is a alpha I VI VI. Okay, Okay, now, so if everything else is 0, then it means that what we have left here, this alpha I, vi, if it add add a bunch of 0 vector equals 0, then like adding a bunch of zeros equals 0, then this has to be also 0. However, we know that since vi does not equal to 0, like vi is not the 0 vector
Yeah.
because we say these are non-zero vectors. So then alpha I has to be 0. Okay, so this vi is basically like any 1 through k. So it means that basically if we are doing v1 here, we know that a alpha 1 must be 0. And we're doing v2
Mhm.
here, alpha 2 must be 0. So basically what we proved here is any I here would be 0. Any alpha I would be 0. So
Yeah.
therefore, if all the factors has to be 0, then this is linearly independent.
Isn't that implied from the get-go by the fact that they're all non-zero vectors? And because they're all non-zero vectors, like unless they cancel each other out, like plus minus
Mhm.
in the when you're taking the inner product sum.
Right, like it basically means that some of the vector is not a linear combination of the other. So for example, v1 cannot be equal to some like 3v2 subtract v4 plus 6v5, something like that. Let's define orthogonal basis. So we define an orthogonal basis of V is an orthogonal system, which is also a basis. So basically, we've already proved that orthogonal systems are linearly independent. And for it to be a basis, we just need this V1 through Vk spans V. Okay, so similarly, we define an orthonormal basis. To be an orthonormal system, which is also a basis. At the base be V1 through Vn. And is an ordered basis. V and for any x belongs to V, then this x represented with the basis B is alpha 1 through alpha n. Okay, and we say if B is a orthogonal basis, then it means that alpha i's equals the inner product of x and vi over the norm of vi. And we say if B is a orthonormal basis, then it means that AI would just equal to x vi. So then we have one definition on the orthogonal complement. Oh, orthogonal complement. So if we say W is a subspace for V, and the orthogonal complement, orthogonal we represent it as W with the orthogonal sign. That equals the vectors in V such that every vector V is orthogonal to the subspace W. So a obvious example is again in R3. So for example, if our W is XY plane, so that's like XY 0, then the orthogonal complement is a span of 0, 0, C. We don't need to write the span because we're using XY instead of like 1, 1.
Yeah.
So this is the XY plane, and this is the Z-axis. Have a proposition saying let W be a subspace of V. Then this orthogonal complement is also a subspace of V. And V is actually the direct sum of W and the orthogonal complement. So this also means that W and the orthogonal complement is a basis of V.